let's just use what we know now to understand how to symmetry decompose a system, this continuous symmetry. And it doesn't really matter where time evolution is discrete or continuous. I'll assume that time evolution is discrete. So again, we have something like that. Is we want to rewrite it in such a way that we pull initial point into the slice, into symmetry reduced space. We pull the final point into the slice, into our symmetry reduced space. It's a space which is n dimensions smaller if the original state space had n-dimensional continuous symmetry. So that we know from studying reduction of continuous symmetries, geometrical reduction. And we want to, again, just impose our condition that the difference of continuous transformations that brought both of these things in is an invariant difference, invariant over all rotations. And you know this. When you have two things rotating, and if you compute their relative angle will stay constant even though you move them. Or if you have two things which are separated by some distance and you change your coordinates by translation, the relative separation will remain the same. Trace formulas are very forgiving because in determinism, periodic orbits are computed on delta functions, and we only need to compute linearized neighborhoods. So it turns out as we change our coordinates, in case of time, the linearized neighborhood will only care about velocity along the trajectory. And in case of group symmetries, they only care about the tangent vectors in the neighborhood of trajectory. So it turns out it only cares about what's called Lie algebra rather than the whole group. So there'll be a whole group transformation, but in computing our volume integrals and changing from original space into coordinates which are designed to, which line up with the parametrizations of rotations, translations, etc., that Jacobian will be only computed by taking first derivative in group. So for example, if you're on the planet Earth, you don't need to know whole transformation to go from here to China. You'll only have to compute in each neighborhood, changing our coordinates, the flat thing, which is 90 degrees to rotation of the Earth. That's called the algebra generator, and in all kinds of obscure courses, this is called angular momentum and stuff like that. That's what it is. Group theoretical notion. And now we want to go, it's a continuous situation. What we want to do is we want to go to coordinates which are transverse to directions of the group. The picture you might have in mind is you have your trajectory doing something, and at every point in the space there is a local patch which can be thought of as a plane in an infinitesimal neighborhood, in which if you apply your symmetry operation, this point will move in n directions. So there's an n-dimensional group tangent space. And if it's a continuous time trajectory, then there is also one particular direction. One of the tangents is the evolution one. And that's the one that we reduced when we reduced continuous symmetry trace formula. But now we want to do the transverse ones to the orbit, which are all the things you can get by moving some point on the orbit and producing all possible copies of it, so-called group orbit. But we only need a little patch in the neighborhood. So again, we'll have a dimension of the state space minus number of continuous directions, translations, dimensional transverse delta function. And there'll be coordinates which are left once I've taken care of these ones. So I can't draw it on the same blackboard, but they're transverse to the group xt times minus g fx times gn. And what interests us is first to take care of the parallel ones. To make sense of it, it has to be a delta function. So what delta function are we talking about? With a group, this group operations that we're talking about, we'll assume that they form e to the some set of angles times some set of matrices. So this is d by d dimensional representation of action of a group on the state space. This is really a matrix. And these guys are either called generators of infinitesimal translations and we are interested in three of them. And if I want to be boring, I can say that's representation of the action of the group on the state space coordinates. And we care about three of those. Let's call them A, B, and each one of them in our particular choice of coordinates parametrization of a continuous Lie group. This one we will call theta A. And maybe we're so clever that that's actually the operation that takes the point in a full state space and brings it down to the slice, the symmetry reduced space. Slice is our choice of one point that represents every group orbit. So we can imagine that's what these guys are. Then we still have a group multiplication. It's still true that that's what it is. But what it means is, this is in general non-abelian group. It depends how you parameterize, etc. There's actually a real calculation to find these three numbers. And this is now E corresponding, this theta can be written uniquely as theta that corresponds to this combination, B minus 1A. So my parameter that specifies where, let's say on a sphere, is G. And I looked at A and I multiplied it by B minus 1. That's some real calculation, but that gives me a unique answer. And I call that answer theta. And reconstruction equation says these two things have to agree. So that's my reconstruction equation. So now the Kronecker delta is not Kronecker delta anymore like it was in the discrete case. It's Dirac delta because these are continuous parameters. And to every value of these continuous parameters corresponds a continuous parameterized state space point. There's nothing discrete about this problem. But now I can go from the original coordinates and I can compute a determinant of where I am in a state space, change to my thetas, and here just have a relation that says reconstruction equation is that I need to compute the difference of these two group operations. And that's now a unique place I end up. But I pay a price of going from lengths to these angles. So you can imagine if this was a circle, then your original x would be a radius of that circle if your group orbit is a circle times the angle on it. So this will dimensionally have to be r, the length, because you have gone to dimensional coordinates, faces, and dimensional. And this is just going from lengths measured, this transverse manifold here, in the neighborhood, I'm going to my angles. So this is my angle, theta 1, and there is angle in every one of the directions. If you really do this very explicitly, you will work with Euler angles, etc. It's very simple for SO2. But in general, you might have to work for every group to produce a group integration variables. And for every of those choices, the Haar measure, the way you integrate over a group, will have some different form, which you compute explicitly if you want to. But the whole point of this wonderful trace formula is you actually never do that in calculation. To make yourself comfortable, you can do it. I don't really want to depend on whatever phase my original trajectory has, because they're all equivalent. So I want to average over all the initial phases. Just like averaged over all initial times and all initial points. We also want to do it in all fundamental domains. We want to do it now. So again, we write a trace, and that has two parts to it. There is a part that's transverse, so n coordinates, n dimensional. And it cares about this part, x2 angles, parallel guys, meaning in the tangent manifold, which is just a plane because we're local. There is integral still to do, which is in the transverse coordinates. So this is in a symmetry reduced manifold, either base manifold or slice, whichever way you do it. What we try to do is we try to stay in the original coordinates. We don't try to have nonlinear coordinate transformations, in which case slice is the right notion. It's just in original coordinates you construct local hyperplanes that do your job transverse to the group orbits. And that's the same. The only thing that you have to remember, it really cares about this angle theta, just like every time before. And then you think about it and you realize that these two things together bring you to the form delta G. So if I change coordinates for transverse things, this Jacobian just takes care of it, and I get a Haar measure, not normalized, unnormalized, dg times this delta function times the rest. Where this is now only depends on the phases, and these are global phases, but we only had to compute one derivative of these phases. So we didn't have to do anything very fancy. We just need to explain the operation that brought A and B into the reduced space or into the slice. For every A and B, which is sitting in this part of integration, it doesn't care which A and B you took, it only cares about the relative distance. So this integral doesn't care about its initial points, it just cares about G. That's what you're integrating here. This is G over theta. And now there are two things to do. Before you took a trace of unity, and you found number of elements. Now you take an integral over Kronecker delta in continuous parameters. And what you find is the volume of the state space. So you find, now this is a volume. So for example, for a circle, this is 2 pi. And what this says is that, okay, I can do my calculation in any symmetry reduced space I want. And all slices are equivalently good, as long as I just take one representative. Uniqueness is important here. There's only one representative for each slice. And I multiply this just by the volume of all possible phase rotations. This is purely group theoretic number. In this, the embedding of group orbit in a state space has gone out through this Jacobian here. So it doesn't depend on the surface or a volume or something, or the physical state space, the way it's embedded in your coordinates. It's only just a number that says for a compact group, I have it. Now, if I'm interested in, let's say, Minkowski group or group of translations, I'll have to think twice, because this will not be compact and I'll have to work much harder to get, sensible predictions. I basically have to develop scattering theory to get sensible predictions. But as long as I'm just looking at compact volumes, compact group volumes, this is doable. So you can do it this way. Or you can, depending on your group, you can write this delta function as the sum of characters. For example, if you have a rotation group SO2, then the sum of all Fourier components adds up to Kronecker delta. So, and that's how the whole theory was intuited in the beginning. This can be either written as a volume, or it can be written as a sum of irreducible representations times their degeneracies of all mu's. And the only difference for continuous groups is that this sum is now infinite, because for continuous group, we don't have a finite number of group elements, so we don't have finite number of classes, so we don't have finite number of irreducible representations. But you should not be afraid of this, because you're very familiar of this already from the work you have done in electrical engineering and in quantum mechanics. Now, in quantum mechanics, here we put irreducible representations of rotation group SO3 when we are doing atomic physics. And in fluid dynamics, we tend to put SO2s or O2s, flips. If we have orthogonal rather than special rotation group, then, but it's just the same as what we did before fusions show up, etc. But it's just the same as what we did before for continuous case. Now, one thing that needs to be worked out, I haven't done it very clearly in the book, is that when we looked at our solutions in a general case of finite groups, we found out that we have to find all the subgroups of our particular group. And each subgroup might have had solutions which have the symmetry of that subgroup. And each one of them had a different factorization. And, it was very beautiful. It was for triangle, there are solutions which were symmetric under the flip, and they appeared 2 times, and there were solutions which are rotationally invariant, but then they appeared flipped, etc. And all of that came in reduction of full dynamics to orbits in a fundamental domain, because fundamental domain, again, will not know, in this case, symmetry invariant space, has no idea that it's part of a bigger game in a big space. Dynamics just takes it. It's just that when you do calculation in fundamental domain, if you weigh them by the characters, you get results for the full dynamics. So reconstruction equation is essential to explain your original problem. But all the calculations are done in a world that doesn't know there is a symmetry, because symmetry has been quotiented out. So now, in this world, the simplest solutions and generic solutions are called relative periodic orbits. So this has support, relative periodic orbits. They have a property that if you start someplace on the orbit, you go a period of the orbit, and you use reconstruction equation to rotate the result back into fundamental domain, you found that in fundamental domain they're periodic. So that defines the dynamics reduced to the fundamental domain. Now, because these guys are parameterized by real numbers, you don't expect any interesting periodicity in the solutions. You don't expect that if you take an orbit and repeat it 3 times, it'll come back to itself. It actually lives on a torus, and it just generically, just ergodically goes around. But if the group is O2, then you expect that there will be solutions which have something to do with the flip. And we remember that the discrete group meant that there were shorter orbits, there were pre-periodic to longer orbits. And when you have a group, like let's say rotation, SO2, rotation on a circle, it has as subgroups also C2, C3. You can imagine you get solutions which are periodic, because that's a good subgroup of the big group. And then they can be rotated by SO2, and so on. So what the book doesn't offer, and I hope you will help me write it clearly, is the classification of all possible solutions of what kind of symmetries they have and how they contribute to the composition of the trace formula here, but also how they contribute to its exponential, which is called spectral determinant, how they contribute to factorization and how they show up. Currently, the factorization says, it looks very simple. It says, I'm acting on the functions defined over the state space, and if the symmetry is, let's say, SO2, I can decompose all those functions in terms of Fourier modes. Because the operator is linear and commutes with the symmetry, then each Fourier mode subspace by itself is an invariant subspace. So it says my spectral determinant is just product of spectral determinants computed on first, second, etc. Fourier mode. And then there's a bit of physics that says you care about the ground states on natural measure. So the 0th Fourier mode is probably the most important. But, I don't have good formulas that say how all possible solutions, and you might not care because you're a gentle person, but if you actually do something like fluid dynamics, solutions do have symmetries and you do have to care about it. There is also an important thing that I have not done any place in the course is that there could be solutions which are invariant on the symmetry group. If you have z-axis and you rotate in a plane around z-axis, points on z-axis don't move. If you do this in 100,000 dimension, points in 67,000 dimensions don't move or something. You can say, well, what do I care? But if you perturb these points, it turns out important solutions tend to sit in such subspaces. It just symmetries like the subspaces. And if you perturb solution in a subspace, either equilibrium or periodic orbit or something, it connects to the whole space. So you do care. It's part of the dynamics in some way or other. And that's also missing from the current expositions. But it will be in Sean Dingell's thesis once it's written.
Can't always get what you want, but if you try sometimes you'll find you get what you need.